Hi, welcome back to this video series on SMT solvers and program synthesis. Today, I'm going to talk about an interesting problem related to integer security. I want to check whether we can safely add two unsigned numbers without overflow. If overflow happens, we wanted to be able to detect that. How can we do this programmatically? So more formally, we are given two numbers x and y. We can assume our numbers are both greater than or equal to 0. What we are trying to do is we are trying to do an integer addition, right? We wanted to be able to add x and y, okay, and we compute the answer and store it to the variable z. Okay, this is not a regular addition. This is unsigned bitwise addition, okay, in a modular fashion, modulo arithmetic. Okay, we can assume both u and both x and y are of size w bit. Okay, so we need w bits to represent x and y. That's the meaning of this addition expression here. Okay, so the question is, can we add x and y and detect that when it is okay to add and when it is not okay to add? Okay, that's basically what we are trying to do in this session. So first of all, I need to explain to you why overflow happens. So let's take a simple example. Let's assume w is equal to 4, okay, which means our bit size is just basically 4 for both x and y. So we have a clock like this, right? Almost a clock, and we have 0 here, and we have all the way until 15 here, because with 4-bit numbers we can go all the way to 15. Okay, this is basically the graphical representation of our numbers. Okay, and as you can see, addition is clockwise, right? You add by 1 means you go clockwise 1 step. Subtraction means you go backwards 1 step. By subtract by 1 means, okay. So why is overflow happening? Let's take a simple example. What is 15 plus 1? 15 plus 1 is actually 16 in regular addition, but the answer is actually 0 in modulo arithmetic. The reason being very clear. 15 is nothing but 1, 1, 1, 1 in binary. And if you add 1 to it, also in binary, right, which is nothing but 0, 0, 0, 1. What will we get? We get 1 and 0, 0, 0, 0. Okay, this is basically what we will get. All right, but we don't have room for this particular bit, so we discard it by just throwing it away. So mathematically, what it means is we get rid of the 2 power w weight, right? Because this contributes, how much does it contribute? This contributes 16, right? Which is nothing but 2 power w, in our case 4. Okay, so to mathematically, to summarize, we add two numbers x and y, and we do a regular addition like in regular math without any modulo arithmetic, and we just subtract 2 power w. Okay, this is basically what we are doing when we add two numbers, and if they overflow, we get rid of the most significant bit. Because remember, when we add two numbers, they may have a carry, and that carry bit will go into the wth position, because remember the index starts from 0. Okay, this is index 0, this is index w. Okay, and the weight for the term, this weight is 2 power w, this weight is 2 power 0. Okay, so and 2 power 1 and so on. These are the weights for the individual terms. We multiply the weight with the binary value and add all of them to get the original number value. Okay, anyway, this is basically the sum of two numbers when they overflow. If they don't overflow, it's nothing but x plus y. Okay, so now the question is, how can we programmatically detect? Many languages do not offer an API to detect whether addition can be done safely or not, so we need to write a little program for that. So I'm going to let automated reasoning come up with a program for us. Okay, so I will show you now such a program that I wrote using the program synthesis technique. So what you're going to see right now is programmatically synthesizing such a unsigned overflow detector. Okay, so let me explain the grammar first a little bit, right? I'm not going to do formal specification of what is the real meaning of adding two numbers and what is the meaning of overflow. I will just train the machine with some examples. So here are the examples, right? Of course, I do know the very basic property that adding two numbers is commutative, which is true even in modular arithmetic. So the program that we are going to synthesize better satisfy this property, okay? And then we train this with a bunch of examples. Okay, what is 8 in hex, which is this regular 8? 8 plus 8 is 16. 16 cannot fit in a 4-bit number, right? For scalability reason, I have chosen only 4-bit, and then I will generalize it easily, okay? So this overflows. On the other hand, 8 plus 7 is 15, doesn't overflow. 1 plus 2 is 3, doesn't overflow. F plus 0 doesn't overflow, of course. F plus 1 overflows because F is 15. 15 plus 1 is overflowing. 1 plus F is also overflowing, of course. 2 plus F overflows. 7 plus 7 is 14, doesn't overflow. So we have a bunch of examples here. I'm not claiming these examples are complete or not redundant and so on, but I felt that this is a good start to synthesize my add detector, right? Remember, the add detector will take two numbers X and Y, and it's going to decide whether I can safely add those two numbers. And I'm actually going to return 0 or 1. I return 1. When can I return 1? I return 1 if there is overflow. I return 0 otherwise. Okay, so let me explain this Boolean to bit vector in a moment. First, let's run this thing and then see what happens. Okay, so here is the program that's synthesized for us. So it takes two numbers X and Y as input, and it gives us back a bit vector of size 4. As I mentioned earlier, the bit vector has only 0 or 1. And now I have to explain what is the meaning of Boolean to bit vector. Boolean to bit vector is basically converting one, and if you remember Boolean algebra, you have true or false. True is converted into 1, and false is converted to 0. This is the purpose of Boolean to bit vector routine that I wrote here, okay? Let me now show you a little bit about that function very quickly. As you can see, if the input is true, it returns 1, otherwise it returns 0. Okay, that's basically it. The reason I need this is that in this semantics, you cannot combine Boolean type with bit vector type, so I need to convert them into one particular type. So the reason is also that bitwise unsigned less than returns true or false. Okay, so I cannot add a true or false with another expression. Although in C language or in other languages, you can do x less than y. You can do something like this easily. You can do x less than y, which is a number actually, 0 or 1, not true or false, and then you can add it with some w, something like that. You can do it, but in this grammar, this is not allowed. So I need to cast Boolean to bit vector type. That's the reason I'm doing it. Okay. Anyway, with that said, let's get back to the output and interpret the output carefully. Okay. So let me clear this and run it. Oops. One moment. Okay. So here is the synthesis program. Let's reason about it. Why is this correct? Our function takes two arguments X and Y, and it is saying all it is doing is basically this. It is adding the numbers X and Y and comparing with X. So it's doing like this, right? It's saying Y less than X. If this is true, what can we say? Well, if it is true, it says 1, because this, remember, Boolean to bit vector is basically converting the expression value into 1 or 0. So this is one part. So this is a expression that we can use to detect whether overflow occurred or not. Okay. Why is this correct, and why can we trust this? Remember, this is synthesis based on examples, okay? But we can still reason about it. I have given a bunch of examples, okay? So the way we can reason about it is as follows, right? If let's assume there is no overflow for a moment, okay? So what can we say about the sum? Now the sum is nothing but, remember, the sum is x plus y, And if there's no overflow, basically x plus y will be greater than or equal to x, and also greater than or equal to y. So we can replace wherever I said x by y. Okay, so this is true when there is no overflow. Okay, so we are all set with that. But let's consider the case when there is overflow. When there is overflow, the problem is if x plus y is less than x. Okay, how can we use this expression to detect there is no overflow? So we can do that as follows. If there is overflow, what is the meaning of bitwise unsigned addition? The bitwise unsigned addition meaning is that we can rewrite this as nothing but regular addition minus 2 power w. This is something we learned from the beginning, that when there is overflow, we just add the numbers and subtract the most significant bit weight. Okay, but we do know that both x and y are w bit numbers. Therefore, x and y both are less than 2 power w. So when y is less than 2 power w, what can we say about y minus 2 power w? In regular arithmetic, this is negative. Okay, y minus 2 power w is less than 0. Okay, which means that if I add an x to it, right, I'm plugging in x to both sides, so we can conclude safely this is less than x. Therefore, this expression is a nice way to detect whether overflow happened or not. Okay, if there is overflow, x plus y, which is nothing but the sum, will definitely be smaller than x. Otherwise, there is no overflow. This is the else part. We want to take it this way, and this is the basically this case is modeled as the case when there is overflow. Okay, it's exactly what this expression is actually doing for us. So we can write simple statement like this. We can all we have to do is if x plus y is less than x, we know for sure there is overflow. Otherwise, there is no overflow, and we can go ahead and implies overflow. Okay, so that's basically what I wanted to show to you. If you don't want if then else statement, of course, you can just use the conditional expressions, right? You could just say implicit if then else statement, right? You can say something like this, right? You're going to check if this is true. You're questioning it, right? And if this is true, this is the true part, which means there's overflow, and this is the else part. So you can write implicit if then else as well. Okay. So to sum up, we are able to programmatically detect whether two numbers can be added without causing overflow using this automated synthesis technology, which helps us to come up with an expression based on the grammar. Okay, one thing we can do quickly is that we can also introduce if then else statement if you want. You could just say in the grammar we could write as simple as this. Let me quickly show the grammar for you. If you feel that the bool to bit vector conversion is a little cryptic, we can directly use the sysgis syntax that allows us to plug in an if then else statement. Okay, so I will show you that in a moment. Just a moment, please. Okay, so here is the one moment. Okay, so all you're going to do is essentially include an if then else statement, right? So I'm going to replace this boolean to bit vector and make it more explicit by if then else statement. The semicolon is a comment in this language, and what I'm going to do is basically introduce an if then else construction, right, which is Boolean expression kind of thing explicitly. Okay, what I'm going to do is if then else, y predicate is, and then start. Okay. As a matter of fact, we don't need all of these. We just need, as we just learned, that only thing we need is checking whether it's less than or greater than, right? So we don't need signed. We can just live with less than. Okay. Let's see what happens now. Hopefully this will work, and it synthesizes. Okay, I made a small mistake. Okay, this is clear. Okay, what line number is that? 15. This matches here, and this matches here, and this matches the start. This matches this. One moment. I will just take this better. This one is better for me. Okay, maybe it's easy if I just plug in this. I'm going to use an if then else statement. That's my purpose now. Okay, should be fine now. But I don't need a shift operation. We just need bitwise add, and then we should be hopefully be able to use all of these automatically. We don't need this. We don't need this. We don't need this and this, and this. Okay, so let's give it a try. Getting the brackets right is the tricky part. What did I do wrong here? Oh, okay, I need one more bracket for the part of the function definition. Okay, so it's going to synthesize something using if then else statement, which we can see it here right away, much more explicit. Let me clear this to make it easy for you to follow. Okay, this is going to use if then else statement explicitly. Okay, so we can see here the program returns 1. When does it return 1? It returns 1 if y plus x is less than y, which is basically what we discussed earlier. So if x plus y is less than y, remember we can substitute y by x, no problem. If this is true, means there's overflow, therefore the program returns 1, implies overflow, that's why it returns 1. Okay, you can assume it's returned. There's no return statement explicitly, but this is basically the if then else part, right? Otherwise, which means x plus y greater than or equal to y, which means the other scenario, no overflow, right? In that case, we say return 0. So this is basically it. Return 0. Okay. So what you're seeing here is a beautiful idea from program synthesis that was able to mechanically derive an expression for us, to detect overflow. Okay, without any human intervention. All, of course, I have to do is define the grammar, right, and explain the type of syntax I would like to see, and then we guide the grammar synthesis to come up with an expression for us. So a couple of important things to note is that sometimes you get into scalability issues if you add a lot of operations in the grammar, right? Because it's exploring this possible syntax it can substitute. Actually, as a matter of fact, the constant is not needed. It'll be much faster if you avoid constants. Otherwise, it's going to try all possible constants that are needed to satisfy your expression. Let's see whether this is true. Give it a try. Hopefully it will come soon. Oh, I need to return the constant because I remember I need 0 or 1. So I think I should make that clear here. Otherwise, the program is not trying zeros or ones as part of the return value. What we can also do is more simple. We usually can add constants that we know are useful constants in many cases. So this should be quick. Yeah, this was quicker. So we allow constants. It will plug in the constants to make it easier for us. There are multiple solutions, of course. Sometimes the constants are helpful, and sometimes they are not, because you're going to enumerate a lot of constants. So I'm going to just leave it like this. Constant bit vector. It's going to try different constants for us to satisfy the Boolean expressions. Okay, it's okay to wait a couple of minutes. It's perfectly fine, isn't it? Because it's giving us something useful. So as you can see here, it was able to come up with an expression like this, right? It was adding x and y, and it is saying if x and y is less than y, you get the answer to be 1, otherwise you get the answer to be 0. Okay, that's basically it. Actually, it's interesting. As soon as I introduced the constants 0 and 1, it was able to use some other expression. It said if 1 is less than y plus x, which actually means something more interesting. Actually, I am going to leave you as an exercise to think about, but for me, it's important to know that I can derive such an expression automatically from the grammar specification. And specifying the grammar is the tricky part, of course. You need to be careful not overwhelm the system with a lot of options and large bit vector size. The reason I picked bit vector size 4 is I can easily generalize as a human from the pattern, okay? And I don't need this thing now anymore because I allowed if then else. And I allow constants and variables, and then I'm done. Okay, so the confidence in this generated expression is based on how good the examples you derived. Okay, you mentioned lots and lots of examples as part of the program. If those examples are not sufficient or not capturing the intention properly, then the generated program may not be perfect, of course. So we need to be careful about that. Other than that, that's mine. We show to you that automated program synthesis actually can be of value for some carefully selected programs. Okay, thank you very much.